All right, we're at the top of the hour, so we're going to go ahead and begin. On behalf of the Environmental Finance Center Network, welcome to our webinar today on wastewater lift station operation and maintenance. My name is Avery Davis from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we'll get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and other information you may need. You can also download the slides and other reference materials from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire webinar and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. And if you have any questions or need assistance, feel free to contact us at smallsystems@syr.edu. Now for a little bit about the Environmental Finance Center Network. We provide training and technical assistance to small water, wastewater, and decentralized systems in all U.S. states and territories through our building technical, managerial, and financial capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. And before we begin, I'd like to quickly highlight our presenter's next upcoming webinar with us, which is Wastewater Collection Systems Operations, Maintenance, and Inspection. This free webinar is taking place on Tuesday, July 16th from 1 to 2 p.m. Eastern. I will drop the registration link in the chat shortly. And on that note, I would like to introduce our presenter for today, Greg Pearson. Greg is a water and wastewater systems trainer coming to us from the Great Lakes Environmental Infrastructure Center. Welcome, Greg. And on that note, I will go ahead and hand it over to you.
Thank you very much, Avery, and welcome everyone to today's presentation. Avery, is my audio and video coming across clearly?
Yep, everything looks and sounds great.
Great, thank you very much, and welcome again, everyone. Today's topic is wastewater lift stations, and we're going to talk about operation and maintenance, but we're going to talk about kind of a variety of other topics related to that as well. Everything from design to safety. So it's going to be a big overview today. And I want to give you an opportunity at the end as well to let us know what aspects of lift stations you'd like to know more details about. And we might be able to get a targeted training that satisfies those needs. And a little bit about where I'm coming from. My name is Greg Pearson. I'm the water and wastewater systems trainer at the Great Lakes Environmental Infrastructure. This is one of the environmental finance centers that partners with the Environmental Finance Center Network. And so we primarily serve Region 5, which is a 6-state region, which also has 35 federally recognized tribal governments. And we have a focus in our training, research, and technical assistance on asset management. And with the new infrastructure funding, we're helping a lot of small systems to obtain and apply for infrastructure funding. I want to start with our first poll, and I'll hand it over to Avery for the poll.
So I am launching the poll now, and the first poll is, how many lift stations are in your wastewater collection system? The answer options are none, 1 to 10, 11 to 20, more than 20, or not applicable to my role. And in that case, feel free to leave a comment using the questions box. Looks like we have about 70% who have voted, so I'm only going to leave it up for a few more seconds. All right, I'm going to close the poll in 3, 2, 1. And looking at those results, it looks like 3% answered none, 30% answered 1 to 10, 15% answered 11 to 20, 15% answered more than 20, and 37% said not applicable.
Okay, well, thank you for your participation. It sounds like we have a lot of operators, managers of systems, over 50% sounds like that have lift stations that you're responsible for in some way. I want to start with a little scenario. This is not part of your slides in your handout, but I added this little scenario. Imagine you're a wastewater operator and you get that 1 a.m. emergency call. And on the other end of the line, there's a voice telling you that the collection system is overflowing. You have manholes that are overflowing, some basements are getting flooded, and all this is occurring on a certain street that you know is upstream of a problematic lift station. So immediately your mind turns to that lift station that's been giving problems. And you ask yourself, what could be the problem this time? Could it be rags clogging the pump? Is it fats, oils, and grease that have clogged a check valve? Is there some sort of power outage? And you kind of dread this situation because you think about this old lift station, how difficult it is to pump it out. And you're dreading the dangerous confined space entry that is probably going to be involved to make the repairs. And you know it's going to be a long day. So you jump out of bed and reach for the light switch. So as we go through, think about these problems because we're going to be discussing topics that relate to responding to emergencies and to maintaining lift stations. So we'll start with the purpose and talk about some design factors. Get your calculators handy or the calculator on your phone because we're going to do some calculations. We're going to talk about some basic inspection and maintenance practices we can start integrating into our practice. A little bit about emergency operations, and finally we'll talk a little about safety. So for the purpose, we have lift stations mostly because we want to lift water from a lower elevation. We have a low point in our system that prevents us from continuing on with our gravity sewer. And so the lift station simply lifts up that water through a force main and the gravity system can continue on. If we were to keep the grade required to allow gravity flow, eventually, if we followed that dotted red line, we would get pretty deep in the ground. And that brings us to the reasons to install lift stations. And the primary reason is that it's just too expensive to excavate so deep, 30-foot deep, 40-foot deep collection lines can get very costly. And also you have to maintain a certain velocity of flow in the collection system, a minimum of 2 feet per second, or 2.5 feet per second is what you're looking for because you don't want solids to settle out in the gravity system. Also, you could have a situation where the soil is just not stable enough to do the trenching and so forth that is required to install a gravity sewer. The groundwater table could be too high, and there's certain situations where you just have 1 or 2 houses that are in a low area, and it's just not practical to install the gravity sewer, all the expense to install the gravity sewer to satisfy the needs of that small area. So there's lots of reasons to install lift stations. And if we look at it through the lens of advantages and disadvantages, the advantages, it avoids that costly excavation and construction. And also you can get the same flow through smaller force main pipelines and at a lot shallower depth. The disadvantages, however, is mostly what we're going to be talking today about in the light of how we can make our lift stations work efficiently and monitor them and assess them. The first disadvantage, if we have an interruption in the power supply, we have problems. We can have sanitary sewer overflows. we have to have emergency backup equipment such as generators and bypass pumps. And that's a whole nother equipment element that has to be maintained. And finally, we're going to talk about this as well. Lift stations create another space that creates hazards for the operators. It's a confined space with all kinds of dangers in it. There's two basic types of lift stations, two categories. There's wet well and dry well. You can see on the left-hand side of your screen a wet well with two submersible pumps installed at the bottom, where the pumps and some of the piping and valves is underwater in the wet well. And then on the right-hand side of your screen, you can see a design where the pumps and the valves have been taken out of that wet well into a dry well. And that you can see that operator can easily access those pumps and check valves to conduct maintenance. It's a little extra expense to install that, but you can see there's lots of advantages to being able to easily access those components. There's another type of lift station that's called the direct inline pumping system, the DIP. And this has some special characteristics. First of all, it has a special impeller usually installed with these that if it senses a clog, it'll reverse and try to unwind the clog. And of course, it has a smaller footprint and there's no wet well. Everything is contained in the pipe. The wastewater coming in is piped in directly to the pumps because it's direct inline pumping and goes through the pumps and right to the force main. The normal lift station, the standard lift station you'll see in collection systems is a duplex pump installations. And of course, you can have more pumps. What you have here is two pumps that can either work together to pump higher flow demands, but can also alternate. And they can also provide some degree of redundancy. One is the lead pump and one is the lag pump, and those are alternated so that you have basically equal wear. You can see the floats there in this system that are used to turn on and off the pump. And you can see some guide rails that are going down so that those pumps can be taken out and in by sliding them down the rails. And we're going to talk about that a little bit more a little later on. And here is kind of a diagram showing a whole lift station and the electronic controls above it. And when you have a float system, the lower floats are for starting and stopping the lead pump, and the higher floats for the lag pump, and the top float, excuse me, is the high alarm. And the control box at the top contains the HOA switches for the pump control and the interface between the floats and the pump operation. And at the top, you can see the red light that is a warning light that lets you know when there's conditions such as a high water level. And there are different systems, depending on the characteristics, will have different standards where they set their alarms and lead and lag. And I'll give you some examples. This is just an example. This might not be exactly how you would set your lift station, but in this case, we have a high alarm that's set 6 inches above the lag pump. So when the lag pump, when that level for the lag pump on, it's the second down from the top. When the water reaches that level, it means that the lag pump, the second pump, needs to turn on. There wasn't enough power, there wasn't enough pumping flow to pump the water down with just the lead pump. So the lag pump turned on, but there's more flow and the lag pump can't keep up for some reason. And so if it gets 6 inches above that lag pump, the high alarm level goes off. And how far above the lead pump would you want the lag pump to come on? Well, when the lead pump comes on at that water level at the bottom of that red arrow, in a normal low flow condition, that lead pump, when it turns on, the water level would go down. But if there's an excessive amount of flow, it would keep rising. Well, how far do you want it to rise before the lag pump comes on? Here's a good example where you could set it to come on if it gets 1 foot above that lead pump. And then how far do we want the distance between the lead pump on and off to be? Well, that's going to depend on a couple different factors. How many times you want your pump to start and stop per hour, and also the volume of water that is in the tank. And the third thing is allowing some cooling water to remain if you have a submersible pump to keep the submersible pump cool. There's some other ways to monitor levels in a lift station. In this example, we're looking at a pressure transducer, and what that's doing, it's placed at the bottom of the wet well, and the water above it is exerting a pressure, and that pressure is converted to a 4 to 20 milliamp signal. 4 milliamps would be the lowest level, and 20 amps would be the highest level, and it tells the pumps whether to come on or not, and what speed to come on if they're a VFD. A third way is ultrasonic. An ultrasonic transducer sends an ultrasonic signal from the sensor down to the top of the liquid surface, and it's measuring the distance between the sensor and the liquid surface. And once again, that would create a 4 to 20 milliamps current normally, and it would tell the pumps when to come on or at what speed to come on at. Here's a little glimpse of what it looks like in the typical collection system lift station control box. You see the warning light on the top, and inside here the components, you have the wiring for the pumps, and then you have the control circuit that goes from the various floats or sensors to turn the pumps on or off, and you also have an alternator that changes the lead and the lag pump. Pump 1 will be the lead, and then after a certain amount of operating time or a certain amount of calendar time, the other pump, the pump B, will be the lead pump. The things inside here that operators would need to do would be, there's a fuse in here, change the fuse if there's a fuse problem, maybe change the lights, check the connections once in a while, and possibly measure current. And most of the other items would be most likely an electrician. You would call an electrician for some of the more detailed items. So let's get into sizing and design a little bit. So the size of a wet well, you're striking a balance between rapid pump cycling while avoiding a long detention time. So a maximum wet well detention time would be 20 to 30 minutes at the maximum. If you had a couple of houses on a wet well on a lift station, you wouldn't install the same size lift station that you would on a giant 24-inch gravity main. You'd have probably a smaller one, a smaller wet well, so that you would limit the amount of wastewater that is allowed to collect in that. You wouldn't let the water collect for a month, in other words, to get up to the level that it would in a larger lift station. So you would size the wet well based on the flow. Also, if you're using VFDs, that changes things. Normally you can lower the detention time to 5 to 15 minutes because that variable frequency drive can cater to the needs of the pumping needs more precisely. It can ramp up to 100%, or it can just idle at a lower RPM, like 25% of the pump power, so it can cater to the needs. Inside the wet well, there's an active volume, and that's really the distance between the lag pump, the upper pump, when it turns on, that's the highest level that it would normally get, and then the lead pump off when it's pumped all the way down until all the pumps are off. That would be your normal operating range, which is the active volume. If you get above that active volume, that's when you have high level problems, and your pumps, for some reason, aren't able to keep up with the flow. And that could happen for a variety of reasons, of course. You're having some kind of problem with your pump, or there's a blockage in the force main, or there's some kind of charging that's occurring from flooding or so forth. Some other design factors would be the expected flows from the homes that are connected and businesses that are connected to that lift station. And you're designing also for a factor of safety by considering peak flows and the possibility of infiltration and inflow, I&I. And also, you're thinking about what are our specs for the maximum number of pump starts per hour? And generally, that's between 6 and 10 starts per hour. So a little note here is that the pumping rate also depends on the diameter of the wet well. You're going to have a higher pumping rate for a 6-foot diameter wet well than you would an 18-inch wet well. And here's another little view with a different set of specs for the setting for the alarm and the lag and the lead pump. 3 to 6 inches, they're setting them apart. But you notice they always leave at least 15 inches, or according to the pump manufacturer, that low water level is for cooling. And there's usually a spec that you'll see in design between the inlet and the bottom. There'll be a certain distance there specified. You want your wet well to be large enough to allow for some outages. And also there'll be a spec that determines how far below the inlet to place the alarm float. Those are all things that you'll see in design specifications. So we're going to do a little calculation here. We're going to do a couple calculations, so you can get your calculators out now. We're going to do a calculation for a lead pump that turns on when the water level is at 40 inches, and it turns off when the liquid level gets down to 15 inches. And we're going to say that this wet well is 6 feet in diameter, and we're going to look at how many gallons are actually pumped in one cycle of this lead pump. So here's the volume of water that we're going to pump. The lead pump starts at 40 inches and turns off at 15 inches. So 40 minus 15 is 25 inches. And that diameter of that cylindrical piece of water is 6 foot. And we'll use the volume formula for this. It's diameter in feet times 0.785. That's 1/4 of pi. And times the height in feet times 7.48 gallons, because we're going to convert cubic foot to gallons. So if we plug our numbers in, 6 foot times 0.785 times 25 over 12. Now you see what I've done there? I took the 25 inches and divided it by 12 inches per foot. So 25/12ths of a foot. That's if it was 24 inches, we'd know it's 2 foot. So this is 2 point something feet, right? Times 7.48 to convert it to gallons. Did anybody calculate that? Put it in the chat if you got it.
I see one answer came in. Wait for a couple more before I give it away. It looks like 3 people answered 440.
Good job. 440, and I added the 0.4 gallons. So that's how many gallons we'd be pumping with one cycle of this lead pump. Now let's do a kind of a thinking analysis here. If we wanted to restrict this to 6 starts per hour, 1 hour divided by 6 is 10 minutes each cycle, and we only wanted to run our pump 50% of the time, or 5 minutes at the most, that would help us to calculate a kind of a minimum pumping rate. So if we took our 440.4 gallons and divided it by 5 minutes, it comes out to about 89 gallons per minute. So our pumping rate here would help us to get an idea of how large of a pump we want. Now we might want a higher degree of safety. We might want to be able to pump that down in 1 minute, which would be more like 440 gallons a minute, right? So that's a little insight into some of the calculations that we can do to assess our design. So we're looking at the average inflow and the peak flow. We talked about that. Another design parameter is the total dynamic head, or the total head that the the pump needs to deliver. And we're going to do some calculations for that. And keep in mind, we also want the flow velocity in our force main to be at least 2 feet per second. We're gonna do a calculation with the minimum flow velocity, but probably the design is going to be a little closer to 5 feet per second. There's a little range there. 2 feet to 5 feet per second would be the range. So if you designed it at 2 feet per second, it's possible you could have problems because centrifugal pumps, the flow is dependent on the head that's pushing against it. So you'd probably want to design a little more than 2 feet per second. And then finally, engineers will compare the pump performance curves to the system curve. And you can see the system curve in this diagram here is sloping upward. In other words, the faster you pump, the more head is pushing back against it. And then you see the pump curve superimposed over that. And I'm not going to try to explain that today. That's a whole nother class to look at pump curves. But we're going to use some simple math to calculate the minimum flow for a 4-inch force main. So we have a 4-inch diameter force main, and we're going to use this equation. The flow in cubic feet per second equals the area in square feet times the velocity in feet per second. Now, to calculate the area, we're going to use this equation. The diameter times 0.785. Now, the diameter needs to be in feet, and we have 4 inches. So we're going to in our minds, 4 divided by 12, that's 1/3, right? So I'm going to round that to 0.3. So 0.33 times 0.33 times 0.785 gives us a cross-sectional area of 0.0855 square feet. Now, we already know the minimum velocity. We're going to calculate the minimum velocity with the minimum velocity, and that's 2 feet per second. Okay, that would be the lowest. So when we plug these in to our equation, we'll find the flow in CFS. Does anybody have the flow in CFS when you multiply the minimum velocity by the area?
I see one answer come in, 2 answers. Give you just a moment to enter these in your calculators. Looks like everybody has, for the most part, 0.171 CFS.
Excellent job. Now, that gives us the flow in CFS. Thank you for participating. You have some fast calculators out there. 0.171 cubic feet. So we got about a fifth of a cubic foot every second. But we want our flow in gallons per minute because remember we looked at that pump curve and system curve, and they were looking at head in feet by flow in gallons per minute. So we need gallons per minute. So we're going to have to convert cubic feet per second to gallons per minute. So this CFS is happening 60 times in a minute. So we're going to have to multiply by 60, and then we're going to have to convert cubic feet to gallons. And there's 7.48 gallons for every cubic foot. So the equation looks like this: 0.171 cubic feet per second times 60 seconds per minute times 7.48 gallons per cubic foot. And I got 76.7 gallons per minute, about 80 gallons a minute for the very minimum flow. Okay. Now, the second thing we're going to talk about is looking at the system head that's pushing back against this pumping system. And the first thing we can do, we look at that diagram at the bottom of our screen, and we see this pipe, this 4-inch pipe. It's 250 foot long. It has a 90-degree elbow. That's going to add an equivalent of 10.1 feet of pipe. There's two 45-degree elbows, and that's going to, each of those are going to add 5.4 feet of equivalent pipe. The check valve adds 33.6 feet of.
Are you still there, Greg? Your audio just cut out for me. Yeah, we're not getting any audio, Greg, just so you know. You might need
The total friction head.
Oh, it's back now. Your audio was gone for a second, Greg, just so you know.
Oh, all right. When did it cut off?
On the previous slide, before one of the transitions.
Okay, sorry about that, everyone. So what we're looking at here, we've calculated the equivalent length of pipe by assigning a certain length of pipe for every fitting. Coming through okay now, Avery?
Yes, and it sounds like you cut out talking about the 45-degree elbow.
Okay, but I'm coming through now, okay?
Yes, your audio sounds great.
Okay, so we added up the equivalent length of pipe for 4-inch pipe for the 90-degree elbow, 245s, a check valve, and a gate valve, and we added those to the 250 foot of pipe that we have. The next slide, we're going to use plastic pipe for this, and we're going to see how much head is added per 100 foot of plastic pipe. And what we'll probably do is we'll look at 4-inch pipe and we'll look at the 100 gallon a minute level. The 4-inch at 100 gallons a minute, that gives us 0.58 feet of friction head for every 100 foot of pipe. So when we plug that in to our equation, it looks like this. We have our 307.2 feet of pipe times that 0.5 per 100. And that gives us a total friction head that's going to be added to the system head of 1.78 feet. So now we can add all of our head together. The total head is going to be the friction head plus the elevation head plus the discharge head. Now the friction head, we just calculated it, 1.78 feet. The elevation head is given to us in the diagram. We're lifting water 10 feet. And finally, we're going to discharge at a PSI of 40 pounds per square inch, and we're going to convert that to head by timesing 40 PSI times 2.31 feet for every PSI. In other words, 1 PSI of water represents a column of water that's 2.31 feet high, or 1 PSI of water can lift water 2.31 feet. So when we add all of our different head levels up, we get a total system head of 104.2 feet. Now, we're going to do one more calculation, and we're going to be done with calculating. We're going to plug this in to a pump horsepower equation. Still coming through okay, Avery?
Yep, loud and clear.
Oh, great, great. So we have to know, to calculate pump horsepower, we have to know the flow in gallons per minute, and we're going to assume 100 gallons a minute. The pumping head, and we calculated that. We added the friction, the elevation, and the pumping head, and we got 104.2 feet. And then the efficiency of the pump and motor, and I'm going to just assume that the entire system has a wire-to-water efficiency of 0.7. And so the equation looks like this. It's the flow in gallons per minute times the head in feet divided by 3960, and then we also multiply the efficiency of the motor. So when we plug our numbers in, 100 gallons a minute times 104.2 feet of head, and then divide by 3960 times 0.7, we get about 3.8 horsepower. Now keep in mind that this horsepower was based on the minimum flow velocity of 2 feet per second. And we had calculated about 80 gallons a minute, and I adjusted it up slightly to 100 gallons a minute. But more than likely, we would design for a higher velocity. So, but this gives us kind of an idea of our minimum horsepower that would be required for that pump. Now, speaking of pumps, this is a cutaway of a submersible wastewater lift station pump. One of the main design factors is that it needs to be able to pass solids of a certain size. The standard is normally the pump needs to be able to pass a 2.5-inch sphere. It has to be able to enter the suction, go through the volute, and out the discharge outlet without clogging the pump. Some pumps can pass larger solids. And also these pumps are sealed so that no water can get into the motor electronic parts, and also the power line going down to the motor is usually specially coated so that it doesn't spark. Also, the impellers can be designed in a variety of ways. There's lots of innovative impellers out there that increase the resistance to clogging, but also there's grinder and cutter pumps that can cut up solids and even rags and shred them so that they can pass through. Now, here's the second poll question. I'm going to turn it over to Avery. Thank you, Avery.
Yeah, so I'm launching the poll now. And our second poll asks, which of the following is the most common operational issue you experience? Pump failures, fats, rags, oils, and grease, check valve or piping failures, electrical outages or component failure, or something else. And let us know your other comments in the questions box. We have about 50% who have voted. Leave it up for a few more seconds. Okay, I'm going to close the poll in 3, 2, 1. And looking at those results, it looks like 8% answered pump failure, 66% answered fats, rags, oils, and grease.
Wow.
The next highest was electrical outages or component failure. And then trailing behind, check valve or piping failures at 6%, and then something else at 4%. And let me hide this and quickly check the chat. Not my field area. Oh, corrosion was another one that was entered in chat.
Oh, good addition to the comments. And the fats, rags, oils, and grease, that could have been separated out, but that's by far the largest nemesis of the wastewater collection operator. I want to talk about a couple of practices you can integrate possibly into your maintenance routine. One is taking time to test the float switches by having a long handled hook where you can lift them up and make sure the correct pump turns on or off when those floats are manipulated, if you have a float system. And at least once a year, you want to clean your lift station. And one of the things that can happen is floats, if you have a float system, they can get coated with grease and make them heavy and not as responsive as they're supposed to be. They're supposed to be light enough to float up with the fluid. Another important practice is keeping track of the hours. The pump station will normally have an hour meter for each pump, and that's very important. Over time, you can look at the number of hours that your pump has run, pump motor has run, as a means to track maintenance and how long pumps last. But also it's important to look at how much wastewater has been pumped. And sometimes when you have excessive hours, it can mean that there's a check valve clogged, or there's some kind of problem with one of the pumps if one has higher hours than the other, or possibly the alternator system. So you can learn a lot by recording those and keeping a track of the record of the hours by date. Also, you'll have a hand-off auto switch for each pump, and on the hand, it's manual. When you turn it on hand, it'll stay on until you turn it off. But on auto, it's running off the floats or another control system. So you can use that hand switch when you do a drawdown test. So a drawdown test, you physically measure the water that's in the lift station and either turn on the pump on hand until it pumps a certain amount of inches or gallons, or allow it to pump for a certain number of minutes. And once you get the gallons pumped and the time, you can take the gallons divided by the time in minutes to get the actual gallons per minute that's being produced by that pump. And you can also use it to compare the pump efficiency over time. You look at what it's actually pumping today based on what it's rated or what it originally pumped when it was new. And you can look at how your pump is performing over time as an additional measure of asset management performance. It's a good idea to have a meter, and normally what's used on wastewater is a magnetic meter, because other types of meters would have to be in contact in some way internally with the wastewater, and most meter types wouldn't fare well. But a magnetic meter, there's no contact, so it's just it's measuring the water atoms passing through the magnetic field. And the meter can also be compared to your meter hour meter readings. Sometimes you can have increased run time where you look at your hour meter and you see, oh, we're getting a much higher hours on the pump than normal. So one of the causes is you can get blockage in the check valve, where the check valve won't close all the way, and it allows water that you just pumped to the force main to flow back into the lift station. So you're pumping it twice. That's one of the main problems. Another problem is inflow and infiltration. If you have a wet weather flow, and it can cause the pumps, of course. And if you just have a lot higher water use or a population increase, you should see that increasing gradually over time. And if you add something like bar screens or grinder pumps, it can actually minimize some of those types of problems. And for fats, oils, and greases and rags, you have to look at the type of problem that you're having. For solids, normally grinder pumps will solve the problem. Fats and oils, though, is kind of out of the collection operator's hands. It's more of a thing where you're looking upstream to work with restaurants and dischargers of fats, oils, and grease, where you're getting them to make sure their grease traps are cleaned more frequently. And finally, rags can be handled with specialized pumps, but also a bar screen that between the inlet and to the wet well and the pump can help to capture some of those. Here's an example of kind of an innovative solution somebody installed in a lift station. They put an aeration system in the bottom of the lift station to break up grease, and they added a bar screen to collect rags. And then you just have to monitor that bar screen and have a long handled rake to remove those rags or whatever else would collect in there. It's a good idea to have a pressure gauge on your force main. And there's two things that can indicate something's going wrong. Increasing pressure over time could mean that you're starting to get clogged up with grease and debris in the force main, and it needs to be cleaned. And the second thing is that decreasing pressure over time could indicate that you have a leak. If you can install a gauge on your force main, it's really a great asset to let you know what's going on. Talking about dealing with emergencies now, a backup generator is very valuable to have. If you can install one at every lift station, that would be great. A lot of systems that are tight on resources, they'll install these at least at the most critical lift stations where there's larger flows and less time to respond with pumping. And it can either be automatically or manually operated. Most have an automatic transfer switch that it senses that when there's a power outage for a certain amount of time, and then it will kick that generator on and you'll have power to the lift station. Another unit is a bypass pumping unit. What you see here is an example of a gas-powered pumping unit. And the thing with these is that you need to do is ensure that you have the right hookups, the piping hookup, because you might be able to lower a suction hose into a lift station, but you want to have some kind of connection to the force main so that that water can continue to go to the force main and to the gravity sewer. Very helpful calculation is time to spill. And there's a nice little diagram here that can help you calculate how much water liquid is in a lift station, or how much capacity a lift station has for additional water. And it goes by the inch. And this could be helpful for your drawdown test as well. So you look at that chart, for example, a 36-inch diameter uh, lift station, every inch represents 4.4 gallons. And so it can also help you predict how much time you have in an emergency to get to a lift station. And so we'll do a little example here. We have a 36-inch manhole, that's 4.4 gallons for each inch. And we have about 96 inches of freeboard before we get to the maximum allowed height. So we have a power outage, and that inflow continues to come into that manhole, into that lift station, and eventually it's going to fill up and will overflow if we don't get there with our mobile pumping unit. And if our current inflow averages about 20 gallons a minute, how much time do we have? Well, first of all, we can look at the volume. We have 96 inches until it gets critical, and each inch represents 4.4 gallons. So 4.4 times 96, 422 gallons. Okay. So how much time do we have? Well, it depends on the inflow. 422 divided by 20 gallons a minute means we have 21 minutes to get to that lift station. That probably is enough time for if you only had one lift station, but what if you had 10 lift stations? 21 minutes probably wouldn't do it. So it really pays to analyze the conditions like this in your collection system, and certain key spots may need to have backup generators, and you can even have a stationary emergency bypass pump installed too. Our last poll here, poll number 3, I'll hand it over to Avery.
For our last poll, we'd like you to answer, how do you handle electrical power outages for lift stations? The options are a mobile bypass pumping unit, backup generators at lift station sites, hire a septic hauler, use a vac truck, or something else, which we would like you to enter into the questions box. About 60% have voted, so I'm going to give you a few more seconds. I'm going to close the poll in 3, 2, 1. And here are those results. It looks like 82% answered backup generators at lift station sites. The next highest was 19% using a mobile bypass pumping unit, followed by 18% who use a vac truck, 11% hire a septic hauler, and 6% answered something else.
I'll be curious to see what those comments are.
Looks like emergency storage, a
Okay.
mobile generator. Cross my fingers that it comes back on.
Okay, thank you for participating. That's really great information. The last little section here we're going to talk about is involving safety. And we're going to talk about a little bit of we started out with design, and we're going to talk about redesign when we get to the end here. But a lift station can be perhaps one of the most dangerous places you can be on Earth, almost. I mean, I know there's places like Iraq that people serve in, and that's not to compare it with that. But as far as workplaces, a lift station is probably one of the most dangerous places that you can be employed to work and have to go inside. Inside a lift station, you have the possibility of insufficient oxygen or oxygen enhancement, which would be, cause fires and explosions to be more likely. If you don't have insufficient oxygen, you could pass out. There's a possibility to have explosive and toxic gases. And of course, walking around lift stations or in them, that's unsafe because it's slippery. There's electrical hazards. There's biohazards, of course, because it's wastewater. And of course, you have the possibility of being engulfed or even having a drowning or being trapped. A very dangerous place. OSHA says that 1/4, 25% of all confined spaces have a one breath death Very dangerous place to be. Besides testing the atmosphere before you go in, you want to have a tester that tests for toxic, flammable gases and oxygen level. But ventilating the confined space is very important to make that atmosphere more safe. And for wet wells, normally you're talking about 12 continuous air changes per hour, and a dry well, if it's a confined space, about 6 air changes per hour. I want to introduce you to something, if you've never seen it before, called the hierarchy of controls. At the bottom, you see PPE. That means you haven't done anything to change the space to make it more safe, but you're depending on personal protective equipment gear, SCBA breathing apparatuses, harnesses, face shields, gloves. So you haven't done anything to change it. The second one, administrative, that's really about changing, training and employing more safe work practices. For example, when you go into a confined space, you're testing the atmosphere, you're having constant communication with the person that's monitoring the work, and so forth. Up at the top, elimination is the complete other end of the spectrum. That means redesigning the hazard so that it's eliminated and it's no longer a physical hazard, completely removing it. So there's a continuum there. And elimination, of course, is the most effective, but might be more costly. And I have a couple of examples here. The first slide here, you see on the right-hand side, you see an operator that's entering into a lift station in a confined space. That operator is having to use PPE. Nothing has really been done much to make that space more safe. On the left-hand side of your screen, you can see a partial solution. There's still a wet well there, but some of the valving has been taken outside into a dry well pit. Still have to go into a pit, but it's a little better. Another way to make a lift station a little more safe, and this is almost standard with lift stations now, but there's still some lift stations out there that don't have that. By having a chain, stainless steel chain attached to the pump and guide rails, you can remove and install submersible pumps into a lift station without having to go inside the lift station. So that's a degree safer. And then finally, this image on the right-hand side, you notice the pumps, the valves, and all of the piping has been taken out of the wet well portion of the lift station, so the operator can a lot more safely do maintenance outside of the lift station. This is a dramatic increase in safety. So we're ending with these thoughts here. And to conclude, some of the things we've gone over, we talked about establishing a regular inspection and monitoring program, or integrating certain aspects into our operation and maintenance so that we can better assess lift station performance. And we talked about being more proactive in preparing for emergencies and some of the analysis that we can do. And lastly, we talked about redesigning to reduce exposure to hazards. And overall, we're advocating, facilitating a kind of a continued learning and infrastructure improvement program that you can bring to your utility. I want to thank you for participating today. If you would, and you'd like to, please share something that you learned today in the chat that you enjoyed learning about or that you might apply and use in your system. And also, we're opening up for questions now. And while you're typing in your questions, I want to make you aware of a resource on the efcnetwork.org site. There's funding tables there that you can click on your state, and it will give you the available loans and grants for infrastructure for your state, both state level and federal level, and includes information about eligibilities and even includes contact information. And finally, I'll leave you with some contacts. There's the Environmental Finance Center Network that you must have found because you're here, But just to remind you, efcnetwork.org, and you can request technical assistance and engage in a variety of resources. And also here at the Great Lakes Environmental Infrastructure Center, you can visit us at gleic.org. And if you'd like to send me any personal questions or email, you can do so at gpearson@mtu.edu. Oh, you've been a great group responding and calculating. It's been a quick hour, and I'll turn it back over to Avery if you see any questions.
I'm looking for questions. I'm seeing a lot of comments. Oh wait, I just saw a question. We have one here. Can artificial intelligence help to overcome lifting stations' dangerous entry of operators, in parentheses, confined space, to protect staff and their family?
Well, I'm going to have to defer that one to Avery or bounce it back to you. I'm not sure, but I'm sure that it will be used in some way. Artificial intelligence probably will be used to analyze risk and maybe monitor flows. And uh, it's a new source of machine learning that
Mm-hmm.
you'd have to have some kind of way to capture data and analyze it. But that's a little beyond my area of expertise. So
I'm also seeing for vents, how do you size those appropriately?
size what?
Vents.
Oh, vents. Yes, that's a good question. Uh, well, I'm not sure exactly how they size the vents. Um, yeah, I'm not sure. But I would look into that. I'd have to ask an engineer. The vent you're talking about, the vent at the top of a lift station. You know, it's very similar to the vents that they put in a house in a plumbing situation to vent the sewer line. And I think the limiting factor would be whether it restricts the air. Um, so you'd want it large enough not to have a restriction, but I don't know the actual specifications. You guys are asking me hard questions now.
I
But
know
I
there's lots coming in.
but if you
Might have
send
to
me
do
an
some more
email,
research offline.
yeah, if you send me an email, I will look them up.
Okay. I'm just real quick, I just want to say if you're interested in the July 16th class, you will need to register for that one using the link that's in chat. I'm seeing some questions about that. You will not be automatically registered for that. I'm also seeing, is the use of VFD operation recommended for wet well pumps?
Uh, I'm not sure if it's recommended or not, but almost all of the newer lift stations I'm seeing that are, especially at headworks, are using the VFD, and the for larger applications because it's so much more efficient. When you have large pumps and when you don't have to operate the pump at 100% capacity every time it turns on, it ends up saving you money over time. For a smaller lift station on a on a regular little small line, uh, it probably wouldn't make as much sense because the VFD is going to be a bigger expense, and there's a lot more controls that go along with it. The difference is uh, when you don't have a VFD, the pump is either on 100% or off 0%. Um, and if it's appropriately sized and you have a duplex pump, I would guess that you're not losing a whole lot of efficiency because you're just turning the pump on until the liquid is pumped down. But if you have a large application with large pumps, I think it makes economic sense in the long term. But I would be willing to get you some more information on that. I did come across some studies on that I'd be willing to share with you if you send me an email.
Great, we're almost at our time, but I'm going to toss you one more question, and then I'll pull the rest of these from the chat afterwards and send them in an email so we can get back to the folks who we did not get a chance to answer their question. So for the last one, What's the best way to get grease out of a scum pit?
A back truck.
Backtrack. Nice and easy, nice and simple answer. And I see a question about a certificate. We will be sending your certificates directly via email, so expect those to come through within 30 days of the webinar date. I want to thank Greg for sharing his expertise with us today. Following this webinar, everyone will receive a follow-up email with the slides, the resource handout, and a link to the recording. We also ask that you complete the evaluation following the webinar, which will pop up automatically. So you can let us know your thoughts on today's session so that we can plan future webinars on topics that are important to you. And Greg, is there anything else you'd like to say before we wrap up for the day?
Well, I just want to thank everyone for being concerned enough about improving their skills at their utility to attend today. And thanks for putting up with all of our audio problems today and for participating so well. And so I look forward to seeing you at the next webinar. Thank you so much.
Great, thank you, and have a great rest of your day. We hope to see you at future EFCN events.